So in this video, we're going to talk about how to graph polynomial functions in factored form. So to graph polynomial functions, we're going to start off by identifying the zeros of the function, then plotting the x-intercepts of the function, plotting the y-intercept, and then plotting additional ordered pairs that are in between the x-intercepts, then consider the end behavior of the function, and then finally sketch the curve. So remember, when we talk about polynomials, we like to talk about the degree. The degree of a polynomial is equal to the highest degree of its monomial terms. So in this polynomial pictured here, you can see that it has a degree of 4 because the highest monomial term has a degree of 4. So we also have this theorem called the fundamental theorem of algebra that tells us that the number of roots of a polynomial is equal to its degree. So for example, f of x has a degree of 3, so we would say that f of x has 3 roots. G of x has a degree of 4, so we would say that g of x has 4 roots. So the zeros of a function occur when you set the function equal to 0 and solve for x. The zeros will tell you the location of the x-intercepts of a function. So if we have this function f of x equals x plus 6 times x minus 1 times x minus 5, we can figure out the zeros by setting the function equal to 0 and then solving for x. So we have 0 equals x plus 6 times x minus 1 times x minus 5. So by the zero product property, that tells us that x plus 6 equals 0, or x minus 1 equals 0, or x minus 5 equals 0. So we can solve this first equation by subtracting 6 for both sides, which gives us x equals negative 6. So we have an x-intercept at negative 6, 0. The second equation we can solve by adding 1 to both sides, which gives us x equals 1. So we have another intercept at 1, 0. Then finally, we can solve this equation by adding 5 to both sides. So that gives us x equals 5, which means we have the third intercept at 5, 0. So you can see that in the graph, it does in fact have x-intercepts at negative 6, 0, 1, 0, and 5, 0. So let's suppose it tells us that the degree of a polynomial function f of x is 4. The roots of the equation f of x equals 0 are 2, negative 3, 1, and 6. Which graph could be the graph of f of x? So if these 4 values are the roots, that means we have x-intercepts at 2, 0, negative 3, 0, 1, 0, and 6, 0. So let's look at graph A. So it has intercepts at negative 3, 0, 1, 0, 2, 0, and 6, 0. So A looks like it's the correct answer. But let's just double check B. B has intercepts at negative 5, 0, 0, 0, and 4, 0. So B will not work. So now you can go ahead and pause the video and try this example on your own. So this polynomial, it tells us that it has roots at negative 1, 2, and 5. So we have x-intercepts at negative 1, 0, 2, 0, and 5, 0. So if we look at graph A, it has x-intercepts at negative 3, 0, and 1, 0. So A will not work. B does in fact have x-intercepts at negative 1, 0, 2, 0, and 5, 0. So that's why B is the correct answer. So we also have this idea called multiplicity. Sometimes when we factor our polynomial, we'll see that a factor appears more than once in the factored form, right? If it appears more than once, it's going to have this exponent next to it. So the number of times the factor appears in the polynomial is called its multiplicity. So the 0 that is associated with this factor will have the same multiplicity. So for example, this polynomial right here, you can see is going to be a 6th degree polynomial, right? So the degree equals 6. So that means we should have 6 roots. Well, you can see when we set this equal to 0, we're only going to find 3 values of x. So the reason that we find 3 values is because some of those values are called repeated roots, okay? So it's going to be repeated the number of times that it is indicated by that exponent. So that's the idea of multiplicity. So the factor x minus 2 has a multiplicity of 2, so that's why the associated 0 at x equals 2 will have a multiplicity of 2, okay? It'll be a repeated root. The factor x plus 1, you can see, has a multiplicity of 3. So the associated 0 at x equals negative 1 will also have a multiplicity of 3. So multiplicity will affect the shape of a graph. So if we have a 0 and there's an odd multiplicity for that factor, the graph will pass through the x-axis at that point. So you can see in this polynomial, x plus 1 to the third has a multiplicity of 3, right? Because it has that exponent of 3. So 3 is an odd number, okay? So that's why at that associated 0, the associated 0 will be at x equals -1. You can see the graph just like passes through, okay? So that's what will happen if you have odd multiplicity. If a 0 has even multiplicity, the graph will look like it's bouncing off the x-axis at that point. So you can see at x minus 3 squared, okay, that has a multiplicity of 2, right? So that is an even multiplicity. And that associated 0 will occur at x equals 3. So that's why at 3, you see the behavior of the graph, it just kind of like has this parabola-like shape. It just kind of hits the x-axis and then bounces off. So odd will pass through, even will bounce off. So another interesting thing is that as the exponent increases, the graph will get flatter at that 0. So you can see at y equals x squared, okay, let's suppose that this is x equals 0. It just kind of hits the axis and bounces off. But as that value of the exponent increases, you can see the graph gets flatter and flatter at that point. The same thing happens with odd multiplicities. So for the lower exponent, you can see the graph just passes through. But as the exponent gets higher, the graph gets like flatter and flatter around that point. We can also find the y-intercept of any polynomial that will occur at the point 0, y. Remember, we said that x equals 0 at the value of the y-intercept. So you can find the y-intercept by plugging in 0 for x into the original polynomial and solving for y. So if we have this polynomial f of x and we want to find the y-intercept, we would say, well, what is f of 0? Well, that would give us 0 minus 2 squared times 2 times 0 plus 3. So 0 minus 2, that's -2, so we have -2 squared. And then 2 times 0 is 0, 0 plus 3. So -2 squared is 4. And then we have 4 times 3, so that gives us 12. So that means we will have a y-intercept at 0, 12, which is what you can see on this graph right here. So we also need to talk about the leading coefficient of a polynomial. So when we have a polynomial, the highest degree term will have a coefficient. That coefficient is called the leading coefficient. So the reason we talk about the leading coefficient is because the leading coefficient and the degree of a polynomial will help you predict its end behavior. Remember, we talked about end behavior. End behavior is what the graph does when it goes on forever, right? It goes on beyond what's pictured in our image that we have. So if you have a quadratic polynomial, okay, remember quadratic means degree 2. And it has a positive leading coefficient, okay? So degree 2 and then leading coefficient is greater than 0. As x approaches negative infinity, y is going to go to positive infinity. And as x approaches positive infinity, y is going to also go to positive infinity. Okay. What if we have a quadratic? Okay, so remember quadratic is degree 2. And then we have the leading coefficient less than 0. Okay, so what if we have a negative leading coefficient? Well, as x approaches negative infinity, y is going to tend to negative infinity. And then as x approaches positive infinity, y is also going to go to negative infinity. Okay, so you see in a quadratic, the end behavior in both directions is going to have the same type of behavior, right? So as x goes to negative and positive infinity, either y is going to both go to positive infinity or y is going to always go to negative infinity. So when we predict the end behavior of a cubic polynomial, okay, remember cubic is degree 3. Okay, and then if we have the leading coefficient, okay, so our leading coefficient is greater than 0, what will happen is as x approaches negative infinity, y will go to negative infinity. As x approaches positive infinity, y will go to positive infinity. So notice that the behavior is opposite in both directions, right? In one direction, it's going to negative infinity, other direction it's going to positive infinity. So same idea, we have a cubic polynomial, so degree is 3, but then the leading coefficient, what if it's less than 0? Okay, if it's less than 0, as x goes to negative infinity, y is going to go to positive infinity. And as x approaches positive infinity, y is going to go to negative infinity. Okay, so once again, we have that opposite behavior. Okay, so for cubic polynomials, as it goes on forever, it's going to go in opposite directions. So we can kind of summarize this, okay? So this end behavior is kind of generalized for whatever polynomial that you have. So you can predict the end behavior using the degree and the leading coefficient of any polynomial that you ever encounter. So if the degree is odd, okay, it's always going to have opposite end behavior. And so depending on whether the leading coefficient is positive or negative, you can see that it goes to negative or positive infinity. If the degree is even, it's going to have the same end behavior in both directions. It's either going to always go to positive infinity or it's always going to go to negative infinity. So this is just another chart that summarizes everything that we just talked about. So the reason we're talking about end behavior is going to help us when we work on sketching our polynomial graphs. Okay, so now we finally have all the background information that we need to work on sketching graphs of polynomials. So we're going to start off by always identifying the zeros of the function. Okay, so we have f of x equals negative x plus 4 times x minus 4 times x plus 1. So we're going to start off setting the function equal to 0 and then solving for those values of x. So when we do that, we get, well, we have x plus 4 equals 0. We have x minus 4 equals 0. And then x plus 1 equals 0. We can solve this first equation by subtracting 4 from both sides. So we have x equals negative 4, which means I have an x-intercept at negative 4, 0. We can add 4 to both sides, which gives us x equals 4. So I have an x-intercept at 4, 0. And then here we can subtract 1 from both sides, which means we have an x-intercept at negative 1, 0. So let's go ahead and plot those 3 points because that is some very useful information that we just found. And now, okay, so we did step 1 and we did step 2. Now we need to figure out the y-intercept of the function. Remember, the y-intercept is going to occur where x equals 0. So now I'm going to say, well, what is f of 0? So that means I'm going to plug in a 0 everywhere I have an x. So I have 0 plus 4 times 0 minus 4, and then 0 plus 1. Don't forget in this polynomial you have that negative in front, okay? So make sure that you keep track of that negative sign. So we have negative, okay, 0 plus 4 is 4, times 0 minus 4, that's negative 4, and then times 0 plus 1, which is 1. So that is going to give us negative 4 times negative 4 times 1, which is 16. So that means this graph has a y-intercept at 0, 16. So that's going to be about here on my graph. So now we need to figure out how this curve is going to look like, right? That's what polynomial functions look like. They have curves, they have up and down values, so we need to figure out where those occur. So what we're going to do is we're going to plot some additional ordered pairs. We're going to pick some numbers that are in between these x-intercepts that we have and use that to figure out what the behavior of our graph is. So remember, we have x equals negative 4, x equals negative 1, and then x equals 4. So if we pick a number that's in between these two values, let's pick a number like x equals negative 3. So I'm going to just remind you of our original function. So that's f of x equals negative x plus 4 times x minus 4 times x plus 1. So if we plug in negative 3, we have f of negative 3 equals negative 3 plus 4 times negative 3 minus 4 times negative 3 plus 1. So when we simplify this, we get negative of 1 times negative 3 minus 4, which is negative 7, times negative 3 plus 1, which is negative 2. We multiply this all out, we have negative 1 times negative 7 times negative 2, which gives us negative 14. So that means we have another point at negative 3, negative 14. So I'm going to go ahead and plot that on my graph. So I have negative 3 and then negative 14, which is about here. And now I'm going to pick a point that's in between x equals negative 1 and x equals 4. So I'm going to pick the value x equals 2. So when I plug that in, I get f of 2 equals negative 2 plus 4 times 2 minus 4 times 2 plus 1. So that is negative 6 times 2 minus 4, which is negative 2, and then 2 plus 1, which is 3. So we have negative 6 times negative 2 times 3, which gives us 18 times 2, so that's 36. So we have another point, so at 236, we have another point on our polynomials. So 2, 36, which is about here. So you notice it's kind of starting to take the shape of a polynomial graph, right? We just have one more thing that we need to figure out, and that is the end behavior, because we need to figure out what's going on as this graph goes on forever. Well, let's look at the degree. So we have 1, 2, 3x, right? So this is going to be degree 3, which is odd. And then our leading coefficient is negative, right? Because we have that negative in front. So leading coefficient is less than 0. Well, let's go back to that helpful chart that we had. Okay, so we said that the degree is odd and the leading coefficient is negative. So that means as x approaches negative infinity, f of x goes to positive infinity. And as x approaches positive infinity, f of x goes to negative infinity. So we can kind of sketch the end behavior onto our graph, right? So in this direction, it's going to go to positive infinity. And in this direction, it's going to go to negative infinity. So now using those x-intercepts and the points that we just added in, we can kind of sketch the graph of this polynomial function, right? So we can sketch, it's going to go up and then turn down. And that is the graph of our polynomial. So now let's try graphing this function. We have f of x equals x plus 2 squared times x minus 3. So we're going to use the same steps that we did before. Start off by identifying the zeros. So we're going to set this function equal to 0. So we have 0 equals x plus 2 squared times x minus 3. Now to solve this, we're going to say each factor then is equal to 0. So we have x plus 2 squared equals 0. X minus 3 equals 0. So we can undo this by taking the square root of both sides. So we have x plus 2 equals the square root of 0. So x plus 2 equals 0. And then subtract 2 from both sides, which gives us x equals negative 2. So we have an x-intercept at negative 2, 0. And then on x minus 3 equals 0, we're going to add 3 to both sides. So when we do that, we get x equals 3, which means we have another intercept at 3, 0. So I'm going to go ahead and plot those 2 points. So we have negative 2, 0 and 3, 0. Now we need to figure out the y-intercept of the function. So to figure out the y-intercept, we're going to plug in x equals 0. So we have f of 0 equals 0 plus 2 squared times 0 minus 3. So that gives us 2 squared times 0 minus 3, which is negative 3. So we have 4 times negative 3, which is negative 12. So that means we have a y-intercept at 0, negative 12. So I'm going to go ahead and plot that on my graph. So I have 0, negative 12. And then now we're going to figure out some additional ordered pairs that we have on our graph. So remember, we have the intercepts at x equals negative 2 and x equals 3. So we need to figure out a point that's in between. So a point that's in between, I'm going to try x equals negative 1. So if we plug in x equals negative 1, we get f of negative 1 equals, I'm just going to remind you of the function, which is f of x equals x plus 2 squared times x minus 3. So f of negative 1 gives me negative 1 plus 2 squared times negative 1 minus 3. So here, that gives me negative 1 plus 2, which is 1 squared, times negative 1 minus 3, which is negative 4. So that gives me 1 times negative 4, which is negative 4. So that means that negative 1, negative 4 is an additional point that I have on my graph. So I'm going to go ahead and plot that, which is about here. And then just to make sure, I'm just going to plot an additional point. So another point that's in between these two values would be like x equals 1. So we have f of 1, and that equals 1 plus 2 squared times 1 minus 3. So it never hurts to plot some extra points, just because it'll give you an idea of what the graph is supposed to look like. So we have 1 plus 2 squared, so that's going to be 3 squared times 1 minus 3, which is negative 2. So 3 squared is 9. We have 9 times negative 2, which is negative 18. So 1 negative 18 is going to be another point that we have on the graph of this function. So we're going to go ahead and plot that on our graph. So we have 1 negative 18. So about here. So we figured out some additional ordered pairs. Let's time to think about the end behavior. So end behavior, we need to start off talking about the degree of the function. So we have this squared, so that means we have x squared and then x. So that's going to be 1, 2, 3, third degree. Okay, so we have a degree 3. And then the leading coefficient is positive, right? So we have our leading coefficient greater than 0. So we have an odd function with a positive leading coefficient. So if we go back to that chart, we have odd with positive leading coefficient this time. So that means as x approaches negative infinity, f of x goes to negative infinity. And then as x approaches positive infinity, f of x goes to positive infinity. So if we go back to our graph, that means it is going to head to negative infinity in this direction, so going down, and then positive infinity in this direction, so going up. And then we can sketch in the rest of our curve using the points that we plotted. Whoops. And then now we have the graph of our polynomial function. So now you can go ahead and pause the video and try this example on your own. So remember, you always start off finding the zeros of the function by setting it equal to 0 and solving for the values of x. So this will give you 3 x-intercepts, which we've plotted on the graph, -3, 0, -2, 0, and 1, 0. The y-intercept can be found by plugging in f of 0, so that gives us -6, so we have a y-intercept at 0, -6. Now we need to find some additional ordered pairs. So we have these 3 x-intercepts. So I first found a point that's between -3 and -2. I plugged in f of -2.5. So that gave me -2.5, 0.875. So I plotted that point next on my graph. And then we found a point that's between -2 and 1. So I did f of -1, which gave me the point -1, -4. I also plotted that point on my graph, so you can see -1, -4. And then finally, end behavior, it is an odd function because we have 1, 2, 3x, right? It has a degree of 3. And the leading coefficient is greater than 0. So that means as x approaches negative infinity, f of x goes to negative infinity. And then as x approaches positive infinity, f of x goes to positive infinity. So that is how we sketch the curve of this polynomial function. So in summary, remember, to graph polynomial functions, you're going to start off by identifying the zeros of the function, then plotting the x-intercepts, and then plot the y-intercept, then find some additional ordered pairs in between the x-intercepts, consider the end behavior of the function, and then finally sketch the curve.